recording now. Okay. Right. So we are going to look at, so this week we are going to look at design and analysis of beams. Okay. So what this topic entail? So what we're going to do, we are going to we're going to look at shear force. Okay, shear force and bending moment. Equations. Okay, and diagrams. Diagrams, I think we have done quite a bit. Okay, but equations, not yet. Okay, we're going to look at this. And then we are going to go into selection of beams. Okay, so after you design your shear force and bending moment diagram, we're going to select the beam. So regarding, let's talk about a bit about shear force diagram and bending moment. Okay, so shear force, what we have is V, yes or no? And the shear force V will generate the shearing stress. Okay. So you all remember the formula, right? Shear is equal to VQ over IT. Okay, where this is the same V. And the shear force is one. I think regarding the topics that I'm teaching you guys, I think the shear force is one of the hardest topic around, and you guys have done it already. Okay, it's over. Okay, but you all still have to remember this when you go for future courses. And then if you look at bending moment, okay, bending moment, and we know already bending moment. Right, bending moment, and this is M, will generate normal stresses. Right, so normal stresses, the formula is stress is equal to my over I. So this is for centric, and for eccentric, stress is equal to P over A plus by my over I. Okay, which we had done last week. Eccentric loading. Okay. So this week, what we're going to do is we're going to go into more detail regarding shear force and bending moment. We're going to emphasize on the equations, and we are going to draw more detailed diagrams. Okay, and there is a few things that you have to remember. Okay, there are a few things you have to remember. So I'm going to do this by working on an example. Okay, we're going to look at an example. Okay, we're going to look at an example on this. Okay, we're going to look at an example. Okay, so the example that I'm going to do is what I've posted online. The link, I hope you all have uploaded the figure. Okay, so this is the diagram that we're going to deal with today. Okay, so what we're going to do is we're going to find for this question. Okay, we're going to look at this question. So we're going to find the shear force and bending moment equation. Okay, so we're going to find the shear force and bending moment equation. Then we're going to construct. Okay, after this we're going to construct the shear force and bending moment diagrams. Okay. Then from here we are going to select. Okay, we are going to select the beams. Okay, select the beams based on bending moment loading only. Okay. For now, we're just going to focus on bending moment only when selecting the beams. On the last week of this course, we're going to combine normal stress and shear stress together. And that is possible through the use of mole circle. Okay, so I'm not taught mole circle yet. So this is slowly a build up. So I've also posted on Avenue to Learn a table like this. Okay, so I hope we'll go into a table, how to use a table like this. Okay, so that is the later part. Okay. So the beam we're going to select, okay, the beam we're going to select is going to be a wide flange beam, okay, for this question. So depending on the question, they can ask you to use a wide beam or S beam or whatsoever, or box beam, okay. So for this case, we're going to use a wide flange, okay. So more important, when I'm doing this example, I'll mention about theories. Okay, so when I start doing the theories, I'll put everything in a box so you know what is a theory. Okay, when is a theory and when and what to remember. So I'll draw a box is the theory that you have to know. But I'm going to work through this based on this example. Okay, so if you look at the example, this is not a simply supported, but we call it a overhanging beam. Okay, so from A to at point B, you have a simply you have a point you have a pin at point D pin. A to C you have a equivalent load, evenly distributed load of 50 kilonewton per meter. So the first thing that we're going to do, number one. Okay, so the first thing we're going to find the reactions at point A, no, point B, right? Point B and point D, right? We're going to find the reactions at point B and point D. And then we are going to look at the equivalent load, which we have taught about before regarding equivalent load. Okay, so we're going to draw this now. Yeah, I'm going to sketch this free body diagram. Right, so on this free body diagram, so you have this is point A. Okay. All right, so we know that at point A, so this is our point A. Over here, this is our point B. And then we have our point C. And then over here, we have our point D. Okay. And we know that we have a reaction at point B. And we have another reaction at point D. Okay. So based on our transformation that I'm going to define, X y, rotation about z. So we have by, we have our dy, then we have our evenly distributed load. Okay, so our evenly distributed load, the equivalent load. So the evenly distributed load we're going to represent by a single equivalent load. Okay, so this single arrow that we are drawing now. Okay, so this single arrow that I'm drawing now is our equivalent load. Okay, so I'll write this down as our equivalent load. Okay, so our equivalent load will be equal to 50 times 10 to the power 3. And we know the distance, right? We know the distance. If you look at it, if you look at the diagram, the distance is 2.4 plus 0.8, which is equal to 3.2. Okay, so this is equal to 50 power 3 times by 3.2 is equal to 160 times 10 to the power 3 Newton. And the next thing that I think we should sort out is also the distance. Okay, I want you all to sort out the distance at the same time. It's important to know that the distance that we are dealing with when we start before we start our analysis. Okay, so we look at the distance. So from here to here, this is equal to 0.8, right? And then the next one from here to here, so it's equal to 2.4 plus 0.8 is equal to 3.2. And then the distance from here to here, right, is equal to what is it? It's equal to, so it's 2.4 plus 0.8 divided by 2, 1.6. If you got the distance wrong, you're gonna be in a bit of a trouble. Okay, we're gonna be in a bit of a trouble. So again, as I said, let's sort out all the distance first, then everything will be easier. Okay, so the first thing we're going to do, as we mentioned before, we are going to find, okay, as I mentioned before, we are going to find, right, we're going to find the reactions at point B, at point D. Okay, so we are going to take, moment. So I mentioned about moment Z. Okay, I'm going to use at point B. I'm going to take my moment at point B. The whole thing will be equal to 0. Okay, so when we take moment at point B, so at moment at point B, the equivalent load is 160 times 10 power 3, and it's going clockwise, right? So minus 160 times 10 to the power 3 multiplied by the distance is 0.8. Right, you all can see y 0.8, right? From A to B is 0.8. From A to the equivalent load is 1.6. So that is why it's equal to 0.8. Then dy is going anti-clockwise, plus by dy, or plus by dy, and then multiply by a distance of 3.2, right? Because we are taking moment at point B, so 3.2. So it's equal to 0. So therefore, you found out that dy is equal to 160 power 3 times 0.8 divided by 3.2 is equal to 40,000. Okay, so 40 times 10 to the power 3 Newton. Then we have summation about forces in the y direction is equal to 0. And why we do this? Because we need to find Py. And we can get the answers for all this because this structure is known as statically determinant. Okay, if the structure is not statically determinant, then we have to use deflection, which I've not taught you guys for deflection. So that will be in after your term test. Okay, so from here we know that we have 40 times 10 to the power 3 plus by By minus by the equivalent load is 160 times 10 to the power 3